Okay, thank you. So first, I'd like to thank the organizers for invitation. I'm very sorry for not being able to come at this time. And so I really appreciate there's still opportunity to join the conference, but unfortunately not the reception. Okay, so today I'm going to share with you our recent work on mass imbalanced fermions. Okay, since the subject of this conference is opportunities and challenges in fewbody physics, so I think one such challenge is actually, I think one challenge in fewbody physics is basically what can we gain from the study of fewbody bound state in understanding the many-body physics. For example, we know in sector we can have dimer or trimer formation, right? So how will this their associated fewbody correlations will affect the many-body system? Actually, there are some typical examples for such effect. One example is for this dimer formation in driving the BCS to BC crossover in the speed one-half fermions. Actually, if you look at the famous BCS answers, this VK part, you will find that this VK term can exactly reproduce the dimer wave function in BC limit. So this is a strong evidence for this the dimer physics here. And also another example is the dimer formation can also drive a polyron to molecule transition in this 1+N impurity system. Actually, there are many studies on such transition in the past decade, and I only list here two original work on using different method to extract the transition point. Okay, I will come back to this later. Okay, so these two examples actually are all from the two-body correlation effect, right, due to dimer formation. So the natural question is, how about the cluster bound state? And actually, this cluster bound state can induce higher body correlation beyond the two-body one. And how will this high body correlation affect the many-body physics? So this is a topic I want to discuss today. So in particular, I will focus on the cluster bound state induced by mass imbalance. Okay, so in the system consisting of light atom here and N heavy fermions. So by changing the heavy to light mass ratio, actually one can achieve two types of cluster bound state. So one is Efimov type, as here. So basically, near randomness, there can be many discrete energy levels, and their energies not only depend on the scattering length, but on body short range parameter. So another type is a universal type. Basically, there is only one single energy level here, and the energy solely depend on scattering length, but not on any short range detail. Okay, so here I list the critical mass ratio in 3D to support different types of bound state, including Efimov type and universal type. And this is the trimer mass ratio, critical mass ratio, and this is for 1+3 tetramer, and this is for the pentamer. And here, for easy comparison, I list here the realistic Fermi mixtures in cold atoms experiment right now, actually with the mass ratio actually ranging from 4 to pretty large, 29. But since this ytterbium lithium has actually extremely narrow Rayleigh space, so it seems that only the first three mixtures are practical for detection in strong Kavli regime, right? So in this situation, only the chromium lithium mixture barely satisfy the the trimer condition. But for the tetramer and pentamer, they cannot be accessed by these fermi-fermi mixtures because of a very large critical mass ratio. Okay, in this sense, the 2D system seems to be more promising to reduce the critical mass ratio for practical detection, as already revealed by these two earlier studies. So today I will report our result of the study of ground-state tetramer and ground-state pentamer in 2D. And also for the 1D case, I think Dmitry Petrov already reported it this morning in the conference, so I will not include it here. Okay, so here's the outline of my talk. So the first part, I will introduce our results of the fewbody clusters in 2D. And for the second part, this is we will discuss how will these clusters affect the Fermi polyron property. Okay, so the last is a summary and outlook. So for the first part, let me briefly go through the model Hamiltonian. So this is basically contact interaction between a light atom and a heavy fermion. And also we can write down a wave function in the center mass frame. Okay? And then we can define a function, F function, from this psi, this 1 plus n body wave function. And we can get this final integral equation based on this F function. So this F function actually is very meaningful and useful. Basically, it's just the wave function in the dimer fermion frame when you integrate out the internal degree freedom of a pair of dimer. Okay, and then we can also prove a theorem that the total angular momentum of the system can be extracted from this F function. So I will not go to the detail of this theorem, and I just show the result we find. So this is a mass ratio, and this is the energy scaled by the two-body binding energy. Okay, so first we reproduce the earlier studies on trimer and tetramer in these two papers. Okay, but I like to emphasize that this tetramer solution is actually an excited tetramer, and we have newly found the ground-state tetramer actually can emerge in a smaller mass ratio. It is very close to trimer case, right? And also the ground-state pentamer can emerge from the ground-state tetramer beyond this mass ratio. Okay, so now actually we can complete the table by adding these two numbers here and here. And really we can find that these two numbers are pretty smaller than the 3D numbers. That means they can be accessed by the existing Fermi-Fermi mixtures now realized in condensed experiment. Okay, so actually we also find that these two new states actually belong to a different total angular momentum channel. It all have total angular momentum 0. So this is very different from the previous work. So these two solutions all belong to the total angular momentum plus minus 1. So the question is, why they all have 0 angular momentum? And why this critical mass ratio for tetramer is so close to the critical mass ratio for trimer? So again, it is very useful to work in the dimer fermion frame. And now we can define a relative momentum between this dimer and the fermion like this. And then we can prove the second theorem, that is the total angular momentum is actually just the summation of this relative angular momentum between the dimer and different fermions. Okay, now using this relation, we can understand the physical origin of different cluster bond state. So let's start from the trimer case. So for the trimer, there's only one dimer fermion line, right? And actually, a numerical calculation shows this relative angular momentum is plus minus 1. So the total angular momentum is also plus minus 1. And this is the twofold degenerate bond state. Okay, so now if you add another fermion here, so there will be two dimer fermion lines. And naturally, one can expect, so their relative angular momentum can be 1 or minus 1. It's just a natural combination. So totally, we will have m equal to 0. So this is a tetramer case. And also, one can expect that once there is a trimer supported in plus and minus 1 channel, immediately the tetramer will be supported, right? Because of this combination. So that's why the critical mass ratio is so close between these two kind of clusters. In contrast, for this excited tetramer, because the total angular momentum is plus minus 1, so the combination is not like this one. So there will be other angular momentum, relative angular momentum involved, like 0 or 2. So apparently, this configuration should have a higher energy, and this should stay in the excited manifold. Okay, so for the ground-state pentamer, actually our calculation show there is 3 dimer fermion line, and the other line actually stay in the 0 channel. So totally, again, this is a angular momentum 0, and because this 0 channel involved, the mass ratio actually it's much higher than this the tetramer and the trimer. Okay, so just now I have shown that different cluster bond states are actually associated with different dimer fermion structures. Right? And the question is, in experiment, how to distinguish these different structures? So in the next, I will show that they can be distinguished from the momentum space correlation pattern of heavy fermions. So for this, one can define n-body correlation of heavy fermions in momentum space like this. So when this small n equal to 1, this is just the single particle density profile in momentum space, right? So when n equal to 2, this is a two-body correlation here, and when n equal to 3, this is the three-body correlation of heavy fermions. So here, different pictures show the different order correlation function for the trimer case, for the tetramer case, and for the pentamer case. And you can see that these different cluster bond states can have different correlation patterns. In particular, so I would like to emphasize that for the high body correlations. So now let's start from this slide. So basically, I want to show to you that for these high order correlations, for example, the two-body correlation in a trimer case, in tetramer case, and the three-body correlation in pentamer case, we can see a spontaneous crystallization of heavy fermions in momentum space. And this crystallization, actually, you can see either this diagonal structure or triangle structure, or this is a centered triangle, right? And also here, I would like to emphasize that this is purely due to interaction with the light atom. And this is very different from the polycrystal. Let me use the laser point. So this is very different from the polycrystal realized recently in experiment. So for this polycrystal, actually, this is for the identical fermions in a trapping potential, right? But here we do not have any information. They just have interaction. So this can be called as an interaction-induced crystal here. Okay. Don't know why. Okay, so this is a short summary of the first part. Basically, we have identified the ground state tetramer and pentamer at different mass ratios, and because this mass ratio is sufficiently low, so they can be assessed by quite a number of realistic mixtures now in co-atom experiment. And also we have analyzed the physical origin of different clusters in terms of the total angular momentum and also the dimer fermion decomposition. And also I have shown to experimentally detect this higher body correlation, one can observe this crystalline pattern in momentum space. Okay, so now, don't know why. Now let me go to the second part. In the second part, I will discuss how this cluster bound state affects the Fermi polaron. So basically, we know for the equal mass case, there is a polaron molecule transition, right? When the dimer correlation dominates, there will be a transition from polaron to molecule. Then the question is, if there is a trimer correlation or tetramer correlation dominate, how will the polaron system behave? How will the polaron system behave? Will there be a transition or a crossover? And what can we still see the crystalline signature here? So this is the question we want to address. And actually we found here, this is just a crossover, but not any sharp transition. Okay, so let me first briefly review the polaron molecule transition for the equal mass. So basically for the polaron regime, it stays in the weak coupling side, and it is well described by the Chavez ansatz. So this is a zero momentum impurity, and this is the induced particle excitation. So physically, it shows a picture of the typical quasi-particle picture. Basically, the impurity can attract many surrounding fermions to form a quasi-particle. Right? But in the momentum, in the molecule side, the impurity will essentially pick up one single fermion there to form a molecule. And to describe this kind of state, we can use the zero momentum molecule ansatz. With the first term is a zero momentum molecule outside the Fermi sea, and the second part is induced particle excitation. And then by comparing these different ansatz, one can find the energy level crossing between different ansatz. And this is the first order transition. Okay, so recently we actually revisit this problem, and we find that one can use a unified ansatz for polaron molecule. So basically, we extend the Chavez ansatz to finite momentum, and we find that when this finite momentum equal to Kf, it can well cover the molecule ansatz. Okay, in this sense, the nature of polaron molecule transition actually is an energy competition between these different momentum state. So this the dispersion curve, we can see this zero momentum, this is the polaron, and the Kf momentum, this is the molecule. And we can see actually it can be a double minimum in some coupling strength regime, and this provide a very natural explanation our molecule coexistence in realistic experiment. And also, this framework can capture the large degeneracy of molecule because only the magnitude of Q is required to be Kf, but its direction is free. So physically, it means the impurity can pair with any fermion on the Fermi surface to form a zero momentum molecule. And this free choice actually can give you a large degeneracy manifold. And this degeneracy cannot be captured by this zero momentum molecule answers. Okay, so we also compare our theory with two experimental data recently and also very earlier from MIT group. And we find our theory actually can fit this experiment in the Rennes regime, but not in the molecule, polar molecule coincident regime. But here we can find our data actually fit the experiment in the coexistent regime, but not in the Rennes regime. So in future, we really hope there can be a more accurate experiment from the using the direct measurement of the residue to test different theories. Okay, so let me come back to the mass imbalanced case. So here, we still use a unified wave function, but up to 3 particle hole excitation. So in this way, actually one can cover the dimer correlation, the trimer, and the tetramer in a single framework. And we can examine their competition in between and see how will the system evolve from weak to strong coupling regime, right? And here I first show the main result. This is a phase diagram for the 2D Fermi polaron. Okay, my internet, this is not stable. Can you hear me? Can you hear me?
Yes, we can hear you.
Okay. So this is the phase diagram for the 2D Fermi polaron in the parameter plane of coupling strength and mass ratio. And there can be two important mass ratio here. One is the emergence of trimer here, and this mass ratio for the emergence of tetramer. Okay, so our main result is that for the mass ratio below the trimer formation, there can be a fourth order transition from polaron to molecule as you change the coupling strength. But however, if you go above the trimer threshold, there will be no sharp transition there. And there will be only smooth crossover from polaron to trimer to tetramer. And this is the main result. So next, I will introduce a different regime in detail. Okay, so the color here is the weight of different order particle terms. So for the polaron part, this is the zeroth order. So there will be so this is dominated by the bear term, right? So for the trimer case, this is dominated by the second order particle excitation. So for the case, it's dominated by the third order particle excitation. Okay, so for the small mass ratio case below the trimer threshold, as you increase the coupling strength, we find a very similar result to the equal mass case. Basically, there's still double minimum competition between polaron molecule, and within certain coupling window, actually this two minimum can be supported. This is double well structure. So this is just the polaron molecule coexistence as shown by the green area here. Okay, so when you go above this trimer threshold, we will see that there will only be one single ground state at momentum 0, and the momentum Kf is no longer the ground state. So we do not find any sharp transition here. But if we analyze the particle, different particle hole terms, we will find the system actually evolves mostly from the polaron regime to the trimer regime. When the so in the polaron regime, the bear term dominate, and for the trimer regime, the second order the second particle excitation dominate. And during this process, the system actually can build up a trimer correlation as shown this in this diagonal structure here. And we also compare the energy between our answers and the trimer answers, and we find actually this P7 answers always has a lower energy than any other answers here. And essentially, this is because this P7 answers actually can well cover this trimer 5 answers. So the relation can be seen clearly by comparing these two different answers. And we can see that there is a one-to-one correspondence between different particle terms. So as long as we can pin down two holes actually at the opposite direction on the Fermi surface, right? And also the different hole configuration can scatter to each other freely in this P7 answers. And this is why this P7 can have a much lower energy than trimer 5. But this kind of scattering is not included in this trimer 5 answers. Okay, so here I just want to show from polymer to trimer, it only can be a crossover, but not a transition because of this very intimate relation between trimer and polymer answers. Okay, if you continually increase the mass ratio, we will find actually the system will undergo a sequence of crossover from polymer to trimer and to tetramer. And during this process, we can see the crystalline correlation gradually built up in this process. So basically, in the trimer case, this is a diagonal correlation. And in the tetramer case, this is a triangular correlation. Right. And here we also compare the energy between our answers and the tetramer answers, and also the trimer answers. And we find, so this energy is always lower than the other two answers. And we can also see the signature of this crossover here from this non-monotonic behavior of this curve. So now the question is, what's the physical origin for this smooth crossover, and how why in the tetramer regime one can build up the triangle correlation? This is because that very similar to the trimer case, in the tetramer case, actually the particle excitations tend to distribute evenly on the Fermi surface in order to maximize the scattering phase space. So basically, these different configurations can scatter to each other without changing the total momentum. So this is how the triangle correlation is built up in the tetramer case, like we find numerically in this problem. Okay, so let me briefly summarize this part. So I think our main result is that we find in the mass imbalance case, the polymer physics is very different from the equal mass case. So for equal mass case, there can be a sharp transition between polymer molecule. Well, here we find a sequence of crossover from polymer to trimer and then to tetra. So physically, this is because the impurity actually behave differently in molecule. So you can imagine the picture that in molecule case, if the impurity want to pair with a fermion on the Fermi surface to form a zero momentum molecule, so it will need to first excite it to a finite momentum minus KF in order to pair with it, right? But in the trimer and the tetramer case, the impurity does not need to change its momentum. It can still stay in the zero momentum manifold, and then to pair with different particle hole excitations, either forming a diagonal structure or forming a regular triangle structure, right? So this is the main difference, and I think this is a key reason why there will be a transition in this when the two-body correlation dominate, but there will be a sequence of crossover when the higher body correlation dominate.
All right, we're at the last 5 minutes.
Okay, perfect. Thank you. So in above, we have focused on how the few-body bound state affects the many-body physics, right? But we can still look at the problem in a different angle. Basically, we want to understand how will the many-body environment, like the Fermi effect, will influence the few-body cluster, right? So in this way, actually, we can go to the few-body limit first, right? And actually, by sending this KF to 0, actually we can reproduce the few-body result in this limit. So basically, by changing the mass ratio, the few-body sector can go through the ground state transition from dimer to trimer and then to tetramer, right? And now, if you increase KF, if you put the few-body cluster in a many-body environment by increasing the particle number of heavy fermions, you will find that for the dimer case, it will have a transition from dimer to polyron. And for the trimer case, it will have a crossover from trimer to polyron. And for the tetramer case, it will have a sequence of crossover from a tetramer to trimer, and finally also to polyron. So that means the many-body environment can indeed destroy the few-body clusters because finally you will all have polyron picture, right? And only, I think only in the strong coupling regime, this few-body cluster can play an important role here to the many-body physics. Okay, so to summarize, I have introduced our recent work on the few-body clusters in 2D, the tetramer and the pentamer ground state, the critical mass ratio, and they can be very relevant to Fermi-Fermi mixtures now realized in condensed atom experiment. And we also analyze how these few-body clusters affect the Fermi-Polyron system. And we find a crystalline correlation in both few-body and polyron systems. Okay, so here's a reference of our work. For future, I list here several open questions. So first is, how about 3D? Because we know in 3D, there's also tetramer and pentamer solutions, right? So the question is, what will be the crystalline pattern there? Because it's a very intriguing situation, because this is a crystallization on a sphere, but not on a ring. So I think this is a very interesting problem. And second one is more practical. It's about the dimensional crossover from 3D to 2D of these clusters. And finally, if we increase the impurity density, so what will our polyron result implicate the many-body physics here? In particular, I would like to mention earlier Monte Carlo studies of equal mass case. So there we can see this polyron molecule transition actually have a strong implication on the transition from superfluid to normal phase, right? But here, so our study show in mass imbalance case, there will be no transition. So everything is a crossover. So the question is, what will be the phase diagram here? In particular, how will the trimer and tetramer correlation affect this phase diagram? So I think this is a fascinating direction to explore in future. Okay, with this, I think I complete the talk today. This is I would like to thank my associate Peng Cheng and postdoc Ruijin Liu. They have done all the tough calculations, and this is a reference of our work. So with this, I would like to thank for your attention. Thank you.
Thank you for that interesting talk and weathering technical difficulties. Do we have questions from the audience?
I think
So I just probably miss this in your talk that when you compared your transition in polaron to molecule transition in Fermi gas with measurement, experimental measurements. So there was a certain discrepancy there. And as far as I remember, there is an alternative theory to that was sort of better with respect to what you showed here. So could you probably elaborate a little bit about your, what is the discrepancy, why discrepancies seen in this case?
Sure. Okay, here. So this slide.
Right.
Okay. Yeah, so we have a detailed discussion in our paper, but here I would like to say that the discrepancy is mainly in the polar molecule coexistence regime, right? So I would say that honestly, the experimental data is not from a direct measurement. So this is from the parameter fitting of a very indirect quantity. Basically, this from the Raman spectroscopy data. But for that data, actually, they use 6 free parameters to fit their data to extract the residue. And also in their the fitting theory, actually the experiment has used has prettily relied on the theory. For example, this one particle excitation and also the zero momentum molecule. So basically in their fitting theory, the molecule actually will occupy near zero momentum, but not near KF momentum. Right. So, but in our theory, actually, we have used the very different dispersion for this molecule by incorporating the large degeneracy. So basically, in our theory, the molecule condenses at final momentum, but in their theory, the molecule condenses at zero momentum. So I think that this is a key reason why our data does not do not match each other. But actually, you can see our data actually can basically in the polar molecule transition point, our data exactly go to zero, right? But the experimental data still have a very large residue tail. But we also compare our theory with the MRT experiment, and we can see basically it's just the opposite limit to this experiment. We can see our data actually can fit the coexistence regime very well, but not in the readiness regime. So I don't know. So I think yeah, in future we really need another experiment to basically to solve this problem, basically to test different theories from accurate and also a direct measurement, but not from an indirect measurement using many free parameters, fitting parameters. Yeah.
Okay, but do you take into account the final temperature of the experiment?
Yeah. We take into account the temperature and also final density and also the trapping potential. Exactly using the parameter in this experiment.
Okay. Okay, thank you.
Yeah, my first question was also about temperature. What's sort of the temperature regime where you expect your results to be valid? And then the second question is related to the effective range. Do you expect relatively large effective range corrections because it's in 2D and for a mass imbalance?
Okay. So Dottie, for the temperature case, it's still related to this result, right? For the temperature, yeah, so this is a good question. Our theory is actually based on this dispersion curve of single impurity, right? So, and we have included the temperature and the finite impurity density effect to this, but we neglect the interaction between impurities, right? So I think that means we need to go to the temperature reasonably higher so basically to wash away all the impurity interactions there, and the impurity just the thermal gas, purely thermal gas. But the temperature cannot be extremely high either, because otherwise it will wash away all the interaction effect, right? So there's a balance between temperature and the impurity Fermi C, and also the interaction strength in this system, right? Okay, so for your second question, for the effective range, I don't know, but I do expect the effective range can affect the cluster formations. But I don't know how much is the effect. And I think, yeah, I think the more practical problem is actually not effective range, but the crossover physics from 3D to 2D. I think this is more relevant to experiment for this for this system.
Thank you.
I'm just curious about the outlook to the crystalline pattern of 3D cluster on a sphere. Could you comment further? I think from experimental point of view can be challenging, or more from the theoretical point of view?
You mean the 3D sphere?
Yeah, because you commented that in that case you wouldn't have the lattice, but something rotational invariant.
Yeah. So I think for me it's just very theoretically attractive. So you can see here. Let me show you the crystallization of here. So in 2D we only, so it's just a plane, right? This is a plane geometry, and the crystallization actually is on a ring, right? So this is just a ring. But for 3D, I think it's more interesting because we can have a sphere of the 3D surface, and the crystallization can be in a 3-dimensional sphere, not on a 2D ring. And so there will be more possibilities for such crystallization. For example, you can still have a triangle on the same plane, or you can have a triangle actually just like a pyramid, right? So I think this is an interesting question to address in future. What will be the exact crystallization in 3D, right? But in 2D, it's just pretty much like that. But in 3D, I just want to emphasize there are more opportunities, more possibilities for the crystallization.
All right. Well, I don't see any further questions, so let's thank the speaker one more time and thank all the speakers from the afternoon session.
Thank you.